So this video is basically on perturbation theory. Now perturbation method in quantum mechanics used for finding approximate solution of a problem by starting from the exact solution of a related simpler problem. The main feature of this technique is to break the problem into solvable and perturbation part. The history of the perturbation theory is very unique. Basically, this method is not created to solve quantum mechanical problems. It's actually created to solve three body or more body planetary motions. It's basically created by Laplace and Lagrange at 18th and 19th century. At that time, the only law they got is the Newton's law, and now Newton's law, as all you know, is telling the interaction between only two stellar objects. But if there are more than two stellar objects, the Newton's law fails to determine the attraction or repulsion forces. So for our solar system, they developed this perturbation theory to solve more than two body planetary motions. In 1927, Paul Dirac evaluated this particular perturbation theory to solve radioactive decay of L particles in quantum mechanics, which is later named as Fermi's golden rule. So this is the history and introduction of the perturbation theory. Perturbation theory are basically two types. One is time independent and one is time dependent, and the time independent is also divided into non-degenerate and degenerate. In this video I am going to talking about only the non-degenerate time independent perturbation theory. Now, as I said earlier, that perturbation theory is an approximate method to solve a desired potential which is slightly different from a potential whose solution we have already get. Let's take infinite well potential. So as we all know, if I state this is an infinite well potential and the length of the well is L, then as we know, the solution of the wave function is root over of 2 by L sine n pi x by L. Now, so this is our exact solution. If I put an bump or distortion in the middle of the well, now it looks different and it's quite tough to solve this kind of potential. So here perturbation theory is very useful to solve this kind of potentials, to find the correction factors of the wave function and the energy eigenvalue. Here basically we divide the Hamiltonian into two parts like this. Now H naught is the Hamiltonian of the, let's say, this infinite well potential. We know this Hamiltonian, and this H prime is the perturbation part like this, and lambda is a correction factor, where later we will use 1 instead of lambda. We are going to put lambda equal to 1 to solve further. Now let's write the wave function into an infinite series of lambda like this. So as you can see, I'm going further, the order of lambda getting bigger and bigger, and this goes to infinity. So here psi n1 is the first correction to the wave function, and like this we are going to write the energy also. So This is the exact solution which we get by solving the normal infinite square well potential. And like this. So now from Schrodinger equation we know that xi, let's take like this, equal to psi. So putting these values in this equation, what do we get? We get h plus lambda, so h naught plus lambda h prime, applying on the infinite series of psi like this, and here and again like this. So now if we equate the equal power of lambda, what do we get? We get h0 psi n0 is equal to en0 psi n0. Now both their coefficients are lambda to the power 0 means 1. Then if we equate for lambda to the power 1 or lambda, we get h naught psi n1 plus h prime psi n0 equal to en0 psi n1 plus en1 psi n0 like this. Now as I said earlier, I am going to put lambda equal to 1 to simplify that. If I go further, let's equate lambda to the power 2. For lambda to the power 2, we get h naught psi n2 plus h prime psi n1 equal to en0 psi n2 plus en1 psi n1 plus en2 psi n0 like this. Now first we are going to solve this for first correction to the energy. Now as you can see, this is the Schrodinger equation for the normal infinite square well. As I said, this is the Hamiltonian of the infinite square well, this is the wave function of the infinite square well, this is the energy eigenvalues, and h prime is the perturbation part. To find the first correction to the energy, we are going to write this equation, which is for the lambda to the power 1. We getting this from by equating lambda to the power 1 and putting lambda equal to 1. Okay. This. Okay. So what we are going to do now, multiply psi n 0 plus psi n0 from left side, and we get like this. This is bra and this is a cat. Okay, as this is a normal constant, so I can put it here. here. Okay, so we get this. Now H naught is the Hamiltonian for the infinite squared potential. Now as this is a Hermitian operator, so I can easily use dagger sin 0 sin 1. I put it here followed by a dagger. Okay, now that sin 0 or all these wave functions or correction terms are normalized by this, we are getting only one. Now as this is an Hermitian operator, so H naught dagger is equal to H naught, so I can easily write this. Now what do we get from this? We get En0 sin 0, as I told you earlier. Get this. So you can see that this is the expectation value of H prime. Okay, so these two terms are equal, so they are cancelled out. So what do we get? We get the first correction to the energy is the expectation value of the perturbed Hamiltonian for the normal infinite squared potential wave function. Okay, so this is how we get the first correction to the energy. Now if we want to find the first correction to the wave function, to find the first order correction for the wave function, at first I write the equation which we get by equating lambda to the power 1. As I told you earlier, psi n0 is the exact solution of a known potential problem which is similar to the perturbed potential problem. Now psi n0 consists a complete set of wave functions. As sin 1 is proportional to sin 0, so I can write any other functions sin 1 in terms of those complete set of wave functions. So now I have to find this coefficient. Here I write m not equal to n. Why I do that? Okay, so this means that this complete set does not consist this particular wave function. I write it because I have the freedom to write this. Why? That psi n1 plus alpha psi n0, if psi n1 satisfy this equation, then this also satisfy this equation. Similarly, if I write psi n1 minus beta psi n0, where beta is some other constant, this wave function also satisfy this equation, and now this gives the freedom to choose this kind of equation. So to find Cmn, what we are going to do now, I am going to put the value of psi n1 in this equation. So this gives us n not equal to n Cmn h naught psi n1 minus m not equal to n Cmn En0 psi n1 equal to, as it is, s prime minus En1 psi n0. Now I am going to multiply psi L0, another wave function, from the left side. Later I will elaborate why I use this and what signifies this psi L0. So by doing this, I get psi n1 minus m not equal to n Cmn n0. This is a constant, so I can write it out like this, and minus psi L0 h prime psi n0 plus en1 psi L0 psi n0. So if L is equal to n means this n, means this wave function. If psi L0 is equal to psi n0 wave function, what do we get? We get that this definitely will be 0. Why? That psi n, I told you earlier that psi n1 does not consist, this does not consist m equal to n. So that's why by the orthonormal condition, which is psi n0 psi m0 m del mn, which is the Kronecker delta, means if m is equal to n, then this gives us 1, and if m not equal to n, this will be 0. So if I choose L equal to n, so this term will blows up and this will be equal to 1. Now that's not going to help us, so what I'm going to do, I use L when it is not equal to n. And psi L0, let's take psi L0 is a wave function from the complete set what I choose or get from the exact solution. So by doing this, psi m, now this is a summation of those wave functions. Now as I choose a particular wave function, so, and this is going to, if this applies on psi n1, we get the coefficient of psi L0. So psi L CL psi L0 h naught psi n1 minus CL En0, and this will be basically CL, which I write it earlier, and this blows up as L is not equal to n, and from the orthonormal condition this is 0, and we get this. Now as h naught is a Hermitian operator, so I can operate this on the left hand side, and this gives us the energy eigenvalue corresponding to the psi L0 state. Let's take it as EL 0, and then psi L0 operating on psi n1 definitely gives CL, as I write it earlier. So En0 minus psi L0 h prime psi n0. So CL equal to psi L0 h prime psi n0 divided by En0 minus El0, and now substitute L with the m, and this gives us summation of m not equal to n psi m0 h prime psi n0 divided by En0 minus Em0. So as now I get the coefficient psi mn, now put it on the equation of psi n1, we get summation of n not equal to n psi n0 h prime psi n0 en0 minus em0 psi m0. So this is the required first order correction to the wave function. If you want to find the second order correction to the energies, then you have to write the equation for which we get by equating lambda to the power 2. Now this is the equation. So now what I'm going to do is multiply psi n0 from the left side and we get this. Now it's not applied on psi n0, we get en0 sin 0 sin 2 plus sin 0 h prime sin 1 equal to en0 sin 0 sin 2 plus, now this sin 0 and sin 1, that sin 1 does not consist sin 0 and the orthonormal condition shows that this will be 0 plus, and this is 1 en2. So these two cancel out and we get en2 is equal to sin 0 h prime sin 1, and the value of, if we put the value of sin 1, we get not equal to n sin 0 h prime sin 0 and sin 0 h prime sin 0 by en0 minus em0, and this gives us sin 0 h prime sin 0 not square over en0 minus en0. So this is the required the second order correction to the energy of the perturbation part. Thank you.